is Piotr Balcer. I'm from Intel, from Data Center Group, which is involved with creating new kind of memory. And let's focus on the title slide for a bit. So byte addressable storage. That's a unique combination. Like there never was a storage medium that was byte addressable and storage. Like so, because storage was always block-based. Even with the recent additions of NVMe standard, that's still block-based. The file system is still there, and you have to access it through the write-read interfaces of the operating system. So the kind of memory that is byte addressable and is persistent is called NVDIMMs. And NVDIMMs provide fast byte addressable and non-volatile memory. They are plain DDR4 DIMMs that slot in directly into the slots for RAM, but the memory is non-volatile. So that's a big deal, because DRAM was always volatile. It perished on the system reboot. And this combination of properties of this type of memory is very unique, and it allows programmers to think differently about how they approach the problem of creating storage stacks. So initially, you always have a database somewhere down below, but to get data from that database, you have to go through various intervening layers. So I have written an example here. So first you have your application that handles the business logic that can be written in various different frameworks. Then you have probably an ORM framework if you are lazy. Then you have to go through the transport layer, which is probably TCP/IP. Some very high performance systems use RDMA, so InfiniBand, for example. Then you have your database, and the database is also a very complicated piece of software that has to go through the file system, and then only then the kernel can access the storage, right? So that's the model of today. NVMe actually changes this model a bit, because you can actually access NVMe blocks through from user space. So the database solution can bypass the kernel, but that's you still have to use the you still have to operate in NVMe blocks. Oops. Okay, so NVDIMMs, persistent memory, flips this model upside down. So now you can actually access your non-volatile memory directly from your application business logic, allowing you to have zero copy data, which is something very novel in software development. And I actually, this is very important here, the transport layer. I marked that as RDMA because persistent memory and DRAM in general is DMA capable, right? So what does that mean? It means that the CPU does not have to be involved in copying the data. So if you have an RDMA network stack with so if you have in your data center RDMA network, then you can actually create a virtual large mapping of storage directly from the nodes. So this is also something that was never possible before. And Intel, how does the Intel fit in here? So you might have heard about 3D Crosspoint. It's currently being shipped in Optane SSDs. Optanes are NVMe implementation of the 3D Crosspoint medium. So they expose the block storage, the familiar block storage interface, to the operating system, but they still have to pay the penalty for having to go through all of the storage stacks I presented before. So NVDIMs create a new tier in all of this. So you have a new type of storage that fit in after the NVMe SSD and before DRAM. So NVDIMs are much faster than NVMe SSDs, and I mean much, much faster. It's like a few orders of magnitude, and I'm not a marketer here. So Intel presented some slides that were, but this is really, you can actually buy current NVDIMs, not from Intel, but from other vendors that have hundreds of nanoseconds access latency. What that means is that you can actually use the CPU instructions, the move instruction, to directly get those bytes you want without going through the operating system, because it's reasonable to stall the CPU for that amount of time. This is actually not some future product, but it's going to come very soon as part of the Xeon Scalable platform refresh. Okay, so let's imagine I have this new NVDIM in my platform, and what can I do with it, right? It's not that easy to actually touch anything on there, because so we have an application that has persistent memory in its address space, and now we have to address it somehow. Well, there is nothing currently available that allows you to use those bytes as storage, because so the traditional way we use memory today with malloc and libc is allocate memory from the operating system using sbreak or mmap. So that is wrapped by the malloc libc, and then we have some kind of pointer to our data. But that really can't work if you have already existing data, right? Because so you allocated something, but where does that something come from, right? Because this has implicit anonymous memory here, right? Because this always comes from either the heap or from anonymous memory given to you by the system. And this actually can be made to work, something like this, but you have to guarantee that you always exit gracefully or you never use your data again. Okay, so to enable that used model for persistent memory, there is a technical work group in SNIA that created a standard how this new type of memory is exposed to the file by the operating system to the applications. So at the very bottom we have our NVDIMs, then we have some drivers, but that's not important. Then we have a persistent memory aware file system, and this is very important component because who can tell me what currently happens when you memory map file into the address space of your application? It goes through the page cache, right? So you have to somehow avoid that page cache because you no longer want that page cache because this memory is so fast that it's no longer necessary. And you don't want to use that much DRAM because, why double the need of that memory? So there is currently an upstream kernel is support for this persistent memory in ext4 and XFS, and on Windows there is in NTFS. Okay, but there is a second problem. So we have those And I didn't mention something. Feel free to ask any questions if I'm skipping something important, because persistent memory is exposed through the file system, meaning that PMEM itself is also exposed as a file by the operating system. So what this means is that the usage model here is that we have normal files, not some weird block devices, but normal files. Then we can memory map them into your application, and then we can normally use them in our code. So in general, persistent memory is exposed as a file, right? So to get that contents of that file to our application, we use the mmap syscall or map view of file on Windows. So the other problem of persistent memory is fail-safe atomicity. It's like ACID in databases. So the data we store have to be atomic. So what this means is that if I have a function that performs some logical function, something. So for example, I have a linked list and I want to append an element to that linked list, then that append is composed of several different operations, and those operations have to be executed in atomically, right? So that we don't get an intermediate state when we reboot the application and resume the linked list operation. This is very similar to threading problems, because in threads you also don't want other threads of execution to see an intermediate state of your application, of your memory. And this is an example of the same problem, but at a different level. So the CPU gives us the warranty of 8 bytes atomic writes. So what we can do is we can issue the move instruction, single move instruction, that stores 8 bytes somewhere in that file. Then we have to flush the CPU caches, because first when you call the move, you store that variable into the cache, and only then you have to flush that memory location so that the memory controller schedules that 8 bytes we just written to be written to the actual storage medium, to the NVDIMM. Okay, so as a result of that, when we copy something or we write something that is larger than 8 bytes, we can have multiple intermediate states. So all of those are possible because the CPU can reorder cache lines, reorder bytes that can be written. The memory controller can write stuff in different orders and stuff like that. So we have to be careful in our programming to always use the 8-byte atomicity and create higher level interfaces on top of that 8-byte atomicity. Okay, so we started with C to solve this problem, to give the programmer the interface to use this new type of memory in a usable way. And we made something called Persistent Memory Developer Kit. It's actually been renamed, so if anyone known this project before, it was known as NVML, Non-Volatile Memory Libraries, but we renamed it. Okay, so this is a reference implementation of the SNIA programming model. And you can see here that we have few things that make the programming for that type of memory a little bit easier. First, we have special type macros. I don't want to spend too much time on C, but I have to explain the basics. Because without this, you won't understand the C++ part. So we have the special type of macros that define the type on persistent memory. So we have a macro called tioid. So if you were worried about macros in C++, then those macros are really truly awful. Because to make this, the tioid, and then be able to do this, it's very, very complicated stuff. We spent like a month trying to do automatic dereferencing like this. But why do we have to do that? Why can't we have normal pointers? Well, does anyone know what is the size of the virtual address space on x86 CPUs? $64 bits. x86, 64 bits. It's at 48 bytes, which translates to 256 terabytes. So the problem here is that the operating system, that's not that much, honestly. You can have petabytes of storage in your server, so that's not that odd. You can have multiple hundreds of gigabytes of DRAM in servers. That's also not that weird. So the operating system cannot guarantee you at what address is the file mapped when you call the mmap syscall. So we have to somehow solve the problem of having pointers that are relative to the beginning of the place you mapped the pool. Well, not really. I just mentioned the 48 bytes as more of an explanation why the operating system can't give you the always the same address, right? But the real issue is that this function does not guarantee you what's the pop variable is going to be, what address is going to that's going to be. Right? And then, because this is where all of the pointers originate from, we have to somehow translate those pointers at runtime to be dereferenceable. Right? We have to be able to dereference them. So what we made, and that might be that's probably the simplest possible solution. There are better ones out there, but we just picked something that worked, and we were sure that it worked, is to make those tioids contain offsets relative to the place we mapped the pool. And then the tioid also contains the identifier of the pool from which it originates. So when I do this, and I have multiple pools open at the same time, so I have multiple files of persistent memory mapped into my address space, and I do this, then I'm sure that I will be able to, at runtime, find what is the place that my pool was mapped at, and then create a real pointer from that, normal row pointer, and then I will dereference this. And notice that this is just a variable, right? How do you get at the type information from a variable like this? It's really not that easy. So that's a digression about how C is difficult. Okay, so another concept to introduce is the root object. The root object is the beginning of your application and that's it. Because when you map your pool to the address space of your application, you have to have the place to begin, to place your structures into, right? So that's the root object. And we guarantee you that the root object is always zeroed, so you have the unknown state when you start your fresh application. You can think about the root object as a root of a garbage collection sweep. That's how I often reference this. Because the root object creates tree-like structures where the bottommost objects are leaves and intermediate objects are nodes. Okay, so to solve the problem of atomicity I mentioned before on the byte atomicity provided by the CPU, we made transactions that allow you to make multiple modifications at a time. So this is a list. This is an example of a list. So first, when we add a new element to a list, we want to allocate a node. And then we want to assign the node a value. Then we have to assign the next of the new node to the first of the existing list, and then override the first element of the existing list. And then we inserted a node. But notice that this all has to happen at the same time. I mean, atomically, from the perspective of different instances of the same application, right? Because if the application were to crash right here, then, and we didn't have transactions, then this will break, right? Because we will have a persistent memory leak, effectively, because the node will be allocated, but we didn't assign it anywhere yet. So it's very important that we wrap those operations into our transaction. And how many of you know what is Setjump and longjump? And how it interacts with volatile variable? Because if you don't know what's the interaction with volatiles in Setjump and longjump, then you probably can't use Setjump and longjump. This is something we learned the bad way. So those transactions are implemented using Setjump and longjump, so that when we, for example, when we fail the allocation, we jump to the abort section. Or, for example, when we do this, and because this is a snapshot, because this transaction, it's written in C, so we can't intercept loads, but we have to instrument each and every memory operation. So this is a snapshot to the log, because this transaction is an AND log, effectively. So this can also fail because we have to have a place for the log. So again, this makes a long jump to the beginning of the transaction and then wraps around to the abort. So this is also not very very nice implementation-wise. Yeah, but we turned that around and then made the C++ version, which is much more user-friendly, because the C version is so error-prone that almost no one can use it except for the few people that implemented it, literally. So we chose the C++ language as not the natural evolution of those C transactional runtimes, and we made this. So we made a much nicer abstraction for the persistent pointers. It's just like a regular smart pointer, but it hides in itself the offset value and the identifier I mentioned before. And this persistent pointer is a valid pointer from the perspective of the allocator concept. So you can use it in the std allocate. So that's important later. Also, we made something we call the p template property, which semi-transparently wraps a type and creates and overloads the assignment operator. So the persistent pointer also overloads that operator, and it allows us to get rid of the odd snapshot in here that had to happen on the C version. I'll also notice that there is we no longer have to use macros to get to the real pointer. We can just implement the reference operator. Okay, so we took advantage of the closure support in C++11 and made much nicer looking transactions without weird C stuff that almost no one knows how to use properly. And yeah, that's about it. And that's all we really implemented as our stable base, right? We didn't implement any of the containers. We didn't enable any of the ecosystem properly. But we started with trying to use the existing standard containers in our projects because the standard containers can take the allocator concept as a template parameter, and then theoretically we can change the pointer type of that allocator to be the persistent pointer. And that's at least the theory, right? Because that's how it's spelled in the standard. In practice, there are various issues with the implementations of that aspect of the standard. And in particular, the GNU libstd C++ is not very good because it just doesn't compile if the pointer type of the allocator is not a real pointer. Okay, so this is how we imagined it will look. And it actually works, right? So you have a standard vector, and you provide it with the allocator of our foo right there, and then we can transactionally update this vector. And we verify that this actually performs very well. But the problem is with all of the more complex containers like maps, and because the map is implemented in LLVM and GNU libc as a RedBlack Tree, right? But that's not in the standard. The implementer can choose what the implementation is actually. So they can, for example, change that RedBlack tree into AVL tree. But if we rely on the standard containers to provide us with the persistency data structures, then we have to ensure that when we have an existing data, that when we upgrade the standard library, then that the same containers still work. So this is the biggest probably problem that we currently have with that approach. And we have decided to abandon this entire effort. Also, there is a second issue with that, in that we have to intercept all of the stores made inside of the transaction to the variables that we want to persist. So, for example, in this case, the implementation of a vector is based on 3 pointers, as far as I remember. So we can easily intercept all of the stores to the pointers because we control what's the pointer type. So we can hook into the assignment operator of the pointer type. But in the implementation of map, in the RedBlack Tree, there is a color value. That color is a bool, red or black. So we can't intercept a store to that bool. And if we can't intercept the store to that bool, then if something happens in a transaction and we roll back, then the color will be wrong of the node. So we don't know how to solve this. We wanted to change the standard in this regard. There is a better option later. Okay, so there are also different ongoing efforts. I don't know if you guys know who is Neil Douglas, but he is very active on, yeah, he does everything. And he's very active on SG14, which is also somehow involved in data structures. And he wants to standardize a low-level fast I/O library so that if you have an extremely fast storage device like an NVDIMM, then you will be provided with some primitives at a higher level of abstraction than we did, but you will be provided, for example, with a single map, right? So you will create a map on a file, and then you will just have the map interface to that file. This is very interesting, but is different than what we are doing. And to solve those problems I mentioned, we forked libc++. libc++ is the LLVM implementation, and made some modifications so that all of the containers actually work in PMM. So, and those modifications are really small. I believe we could probably push them through the standardization, but I don't really want to do that. So we will probably start implementing those containers from scratch, because we can optimize better if we know that the target of those containers is persistent memory. That's the primary reason why we chosen this, and there won't be any issues with having to go through a committee and then having the standard modified in 10 years or later. So we just want to have something that works right now. So we will probably be implementing some of the data structures. This thing stopped working. I have an update from IT. Okay, sorry. So to show you how we can differently approach the problem of transactions, I want to make a digression for a minute and present to you the transaction memory extensions for C++. Transaction memory is effectively optimistic locking. You can begin an operation without any locks, and then either if you have a hardware implementation like the transactional synchronization extensions for the x86, then the hardware will ensure that those operations are executed atomically in terms of visibility to other threads. So in other words, the E in ACID, isolation. So this provides isolation, but it also has a software implementation. If you don't have a CPU that supports TSX or something different on different architectures. So this is actually very advanced, and the proposal is it's mature. I don't know when they are going to push that forward, but I think they want to have this in standard very soon. But at least I hope so, because this will help us tremendously with our own transactions. Because what it will allow us to do is to transparently intercept the load and stores within a block like this. So we will be able to get all of the modifications and loads to variables that happen inside of the atomic block. And this fits perfectly with our implementation of transactions, because now we don't have to have any of the P templates, because we don't have to overload the assignment operator. We can just transparently instrument a given piece of code that is inside of a transaction. This also could enable us to implement RedLog transactions, because underlogs have this funny property that when you have to store something, you have to call a function that snapshots the previous value of the variable you want to assign to. So this is this function. But to make sure this function, the storage snapshot that is actually on the NVDIM, there has to be a cache flush. Cache flushing is very expensive. And you also have to have a fence, because you have to wait until that flush actually happens, because the new flushes are actually non-serializable, so you have to have a fence. Fencing is also very expensive. So with store and load instrumentation, we could implement red logging. And we want to actually, we very hope that this will actually get accepted, and then we can write our own technical specification for persistent transaction memory. We don't want to actually modify what they have, because that will probably add another 10 years to the effort they are making. So we don't want to do that, and they probably don't want that also. So we want to write another proposal, but that is heavily influenced and based on the work they are doing. And we want to also write our own set of containers that might not be direct copy of the current standard containers, but they will look similar, and we hope to make them work with standard algorithms, for example. And we also want to support independent committee efforts, like the one I mentioned by Neil Douglas. Okay, so that's one of my last slides. I want to encourage everyone to get involved if the topic seems interesting. We are also hiring, so if anyone wants a position. Yeah, that's all I had. Questions?